One of the joys of travelling in France is always to find a nice restaurant and sit for the evening and enjoy the meal. Often the best way to get good value for money is to have the set meal. It tends to be a particularly good price, and of course to enjoy a bottle of wine with it. How many bottles of red wine would the restaurateur expect to sell during the course of the year? Well, think of any demand curve. The demand curve is a function of the price of the good. So the amount he sells depends upon the price he charges for the wine. But as with any demand curve, it doesn't only depend upon the price of the good itself, it depends upon the price of the substitutes and the price of the complements. Here, perhaps the most important substitute is the price of the white wine. If he puts the price of the red wine up, people switch into white. If he puts the price of the white wine up, people switch into red. So the demand for red wine is a function also of the price of the white. It also depends upon complementary goods. In this case, the meal itself. If he raises the price of the meal, then fewer people come into the restaurant. So he finishes up selling less white wine, but also less red wine. So we're looking at these relationships, thinking about the demand for the good, but seeing how it depends not only upon the price of the good itself, but upon the complements and the substitutes as well. The best way to examine these relationships is by partial differentiation. Think about the diagrammatic representation of demand curves. We know that when we change the price of the good, we move along the demand curve, but we hold constant all the other variables. We seek to see what happens when one variable changes, holding all the other variables constant. That's exactly what partial differentiation does for us. We differentiate holding constant all of the other variables that could affect the demand.
Here we'll use the technique of partial differentiation to understand the demand for a restaurateur's house red wine. What determines the amount that he will expect to sell? Well, from sales in recent months, we've estimated that the demand for this red wine at the restaurant will be QRW equals 200 minus 2PRW plus 0.5 PWW squared minus 0.25 PM, where QRW is the quantity of red wine in terms of the number of bottles sold. PRW is the price of the red wine in euros. PWW is the price of white wine in euros. PM is the price of the meal in euros. Currently, PRW is 10, PWW is 10, PM is 16, then QRW equals 200 minus 2 times 10 plus a half 10 squared minus a quarter times 16, which equals 226. So given that the current price of red wine and white wine and the price of the meal, he's selling 226 bottles of house red each week. Now we can seek to know what happens if the restaurateur changes prices. In order to do that, we need to calculate elasticities of demand. We'll start with the own price elasticity, the demand for red wine with respect to its price. To find this, we partially differentiate our demand function, treating everything as constant except the price of red wine, with respect to the price of red wine. So QRW equals 200 minus 2PRW plus 0.5 pww squared minus 0.25 pm. So the partial derivative dqrw by dprw equals minus 2. Now the elasticity is given as PRW over QRW times dQRW by dPRW. So that gives us 10 over 226 times minus 2, which equals minus 0.088. So the negative sign indicates a sloping downwards of the demand curve, but our partial differentiation establishes the value of the elasticity. Roughly speaking, a 1% price cut would lead to a minus 0.088% increase in the quantity of red wine sold, ceteris paribus. Now we can see what happens to the quantity of red wine that he sells when something else changes. Let's think about the price of white wine. Here we need the cross elasticity of demand. The demand for one good when the price of another good changes. To find the cross elasticity in this case, we partially differentiate our function with respect to the price of white wine. Again, ceteris paribus. So let's go back to our original equation. QRW equals 200 minus 2PRW plus 0.5 PWW squared minus 0.25 PM. Now let's partially differentiate dQRW by dPWW is equal to PWW. That is, 2 lots of 0.5 equals 1 PWW. So our cross elasticity is PWW over QRW times dQRW by dPWW, which equals 10 over 226 times 10 equals 0.44. So the positive sign indicates that red and white wine are substitutes. The closeness of the substitutes we found by partial differentiation. Roughly speaking, a 1% rise in the price of white wine leads to a 0.44% increase in the quantity of red wine demanded. So if, say, the cost of his white wine increases and he has to raise its price, he knows how much more red he needs to stock. Finally, let's see how sensitive the demand for red wine is to changes in the price of restaurant meals. Again, we need to find the cross elasticity. This time we partially differentiate our function with respect to the price of the meal. Again, ceteris paribus. So dQRW by dPM equals minus 0.25. Our cross elasticity is PM over QRW times dQRW over dPM, which equals 16 over 226 times minus 0.25, which gives us minus 0.0177. So that negative sign indicates that red wine and meals are complements. The closeness of the complementarity we found by partial differentiation. Roughly speaking, a 1% rise in meal prices will lead to a fall in the amount of red wine sold of 0.0177%. So that partial differentiation has enabled us to isolate the effect on his variables of changing any one particular variable.